Hi there and welcome to tutorial 14 on sample space and Venn diagrams, and this is for the Edexcel S1 A-level module. It is applicable to most other exam boards though, and as always if you're looking for further help do check out youtube.com/Mr. Arnold's Maths. Okay, sample space diagrams are something that we would have come across before at GCSE, so we'll just have a fairly quick recap on how to draw a sample space diagram, and then we'll try a couple of examples, then we'll get on to some Venn diagrams. So suppose that I have two dice and they're rolled, and then we add the scores together. And I'm asked to show all the outcomes in a sample space diagram. Well, I can basically do a two-way table such as this, where I have dice 1 here on the this column, and dice 2 here is on the this row. And what I do is I add the scores together for each intersection. So 1 plus 1 gives me 2. Say here this is 3 plus 3. Here would be 5 plus the 3. And I could just fill in all the possible outcomes for this scenario. So suppose I was asked to work out the probability of getting a 6. All I do is count the number of times that 6 will appear. So once, twice, 3, 4, 5. So it appears 5 times in my sample space diagram. And how many outcomes are there altogether? Well, if you counted up all of these boxes, we would find out that there are 36 outcomes altogether. So the probability of getting a 6 is simply 5 out of 36. Now this little dash here, this apostrophe means complement. Complement. And basically it's another way of saying not. So what we're seeing here is it's saying what's the probability of not getting a 6. So what's the probability of not getting a 6? Well, there's two ways of doing this. One way is to add up all of the rectangles that are not 6s and then put them over 36. Another quick way of doing it is knowing that, well, the probability of not getting a 6 is the same as 1 minus the probability that I do get a 6, which is going to be 1 take away 5 out of 36, which is simply 31 out of 36. And let's just confirm our answer. So let's just count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So that confirms our answer. There are 31 possible outcomes that are not a 6. What's the probability of getting a 1? Well, again, if we look in our sample space diagram, which shows all possible outcomes, we can see that there's absolutely no chance of getting a 1. So that means that the probability of that happening is a 0. And the probability of getting more than an 8, well, all I do is I look at all possible outcomes that are bigger than 8. So 9, 9, 9, 9. We've got these 3 10s. And we've got these 2 11s and finally the 12. So counting these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of getting more than an 8 is 10 out of 36. Right, time for you to have a go. So here's a question now. Pause the video and see if you can work out these probabilities using a sample space diagram. Okay, hopefully you've had a go at that. Fairly straightforward. So your sample space diagram should look something like this after it's drawn out, and then the probabilities are given as follows. Now you might notice something here, 3 over 48. That could be simplified to 1 over 16. It's not a big deal to leave your fractions as they are. You don't always need to simplify. It makes it slightly easier, I feel, when you leave the probabilities all to the same denominator. Okay, so that's sample space diagrams and two-way tables, so it's a fairly straightforward and nothing relatively new there. But let's take a look at Venn diagrams. Now, you might have come across these before, maybe for doing LCM and HCF, but they can also be very, very useful in probability. So let's take a look at the first one here. So suppose I have this Venn diagram, and basically this is event A represented by this circle or sometimes an oval. This is event B represented by this circle or oval, and everything around it is the absolute total sample space. And the total sample space, let's make a little note here, in fact, let's write it like this: the total probability of the sample space must equal 1. Okay, because the probability of of a given scenario must always add up to 1. The total probability of a given scenario must add up to 1. So it's important that we understand this type of notation and we know what regions various probabilities represent. So the probability of A is going to be found in this region here. So all of A. So I can just shade it in. That would represent A. Similarly, we can look at the probability of B by shading in this region. So all of B, that's what's represented by B. Moving on, we now have the probability of A union B. And the probability of A union B is everything in A and everything in B all together. So that represents the two circles fully shaded in. And this can be applied to 3 circles or 3 ovals. So that is the probability of A union B. So it's all this space in here. Now this symbol here, which is a little bit like an N, means intersection. And that means the probability that both A and B occur. So we're talking about this region in here. So that's A and B occurring. So the intersection of the two circles or ovals. We have this, A complement. So that's everything in the sample space that is not A. Okay, remembering that the complement means not. So everything that's not A. So I can shade absolutely everything except for what's in A. So shading the whole sample space with the exception of A. And similarly, we could have the probability of not B. And not B means everything except B. So we can shade absolutely everything in our sample space except B. It's really important that you understand this type of notation because it makes the problem solving later on a whole lot easier. So that's the probability of B complement. Everything in the sample space with the exception of what's in B. Couple more to do. Here we have the probability of A complement intersection B. So what this is saying is everything that's in B but not A. And that leaves us with this section here. So that's everything that's in B but not A. Probability of A complement intersection B. And similarly, we can have the probability of A intersection B complement. So that's everything that's in A, but not B. And that leaves us with this region here. Okay, what if we were given this? A intersection union B. Now, this one can be quite difficult to explain straight off the cuff, but I think it's far easier if we look at A complement on its own and look at B on its own, and then we combine the two. So if you remember from earlier, this is A complement, so everything that's not in A, and this is B, which is everything in B. So to get the probability of A complement union B, what I can do is I can actually overlap these two sample spaces, and that will tell me exactly what region we're interested in. So the probability of A complement union B is everything with the exception of the white region from this diagram here. So we've got all this area here, this area here, and all of up here. So I find it's quite easy when you're dealing with these union ones, maybe look at each one individually and then see what happens if you overlap the two. In a similar vein, we could have the probability of A union B complement. And again, if we look at the probability of A individually and look at B complement individually, that will help us to visualize what this will look like. So if we take A and then take B complement and put them on top of each other, we can see now that it's going to be all of this region here. So everything in A, we've got everything that's not A or not B, or in other words, the outside. And we've also got the intersection part. So you can shade the whole lot in. My shading isn't great today, but hopefully we get the idea. So that is A union B complement. Okay, and one last thing on Venn diagrams before we do a couple of examples, and this is the addition rule. So suppose we talked about the probability of A union B. Now let's take a look at the probability of A again. So the probability of A is this region in here. So that's the probability of A. So we've got everything in A. We've also got over here on the right hand side, we've got the probability of B, which is everything in here. So when we do A union B, let's see what happens. So I'm going to group this together. And let's group this together. And if I take both diagrams and overlap them, you might notice something. The color change that I was hoping didn't quite happen there, but you might notice that I've actually counted this region twice. That's very important that we realize that this region has actually been counted twice. So the probability of A union B is in fact, well, we had the probability, we had A and we added B to it. But what happened? We also had this region, we had this intersection. We had this intersection added twice. I don't want it twice, I only want it once. So I'm going to take away the intersection. I don't want that region counted twice. I only want it counted once because I have this region. What I really want, what I'm interested in is this region and this region and this region. But when I overlapped the two diagrams, let's do that one more time. Excuse me, let's do that, try that again. When I overlapped the two diagrams, we lost a piece. We notice that the intersection part, there it is once, but now it seems to, it's coming in again. I'm adding that intersection bit twice. I don't want that twice, so I'm going to take that intersection away. That's a really important feature with Venn diagrams. Okay, so let's put it into practice now. Have a look at an example. So I'm told that a school has 97 students in year 12. It tells me that 55 take maths, 32 take chemistry, and 31 take neither. And I'm asked how many take both. So let's label my Venn diagram here. So let's call this maths. So this circle here will represent maths. And this can be chemistry. So this circle here is our chemistry. Right, I'm told that maths has 55 students. And chemistry has 32 students. I also know that my sample space has 97 students. That's coming from here. The total number of students in the sample space is 97. And I'm told that 31 take neither. So let's call this, well, I know that 31 take neither. So that means 31 students are on the outside here. Now, how many students, if I add maths, so if we think about it like this, if I look at maths, that's going to be given as 55 out of 97. So 55 out of the 97 students take maths. That's the probability of finding a student that did maths. I also know that a student that did chemistry is going to be 32 out of 97. Now, what happens if I add these two together? Remember, the probability of M union C equals the probability of M plus the probability of C minus the probability of M intersection C, because this bit gets counted twice. So let's see what happens. Probability of M is 55 over 97. Probability of C is 32 over 97. Let's not look at this for a second. M intersection C. That means that if I add probability of M and the probability of C, I get 87. 87 out of 97. And if I add the 31 students that are not involved, so M intersection C, if I add the students that were not involved, so 87 over 97, and I add the 31 out of 97, that gives me a grand total of 118 out of 97. But there's only 97 in the whole sample. The total probability of the situation must equal 1. That means the bit that was counted twice, this bit, must equal, let me see, if I take 97 away from 118, that gives me 21. 21 people were counted twice. So I can say that the probability of M intersection C equals 21 out of 97. So this intersection part is 21. Now if I know that there's 21 people here, but in maths there is 55 altogether, so the whole thing is 55, but this bit is 21, that means if I do 55 take away 21, I get this bit. And 55 take away 21 is 34. And similarly, for chemistry, I know that 21 are taking chemistry here, but there's 32 people in total. That means 11 people must be in here. So if I'm asked how many take both, I know that there's 21 people are taking both. And I can double check my answer. Let's double check, make sure everything adds up. 34 and 21 is 55, so that's good. 21 and 11 is 32, so that's good. I know that 31 people take neither, that's okay. And if I add them all together, 34 plus 21 plus 11 plus 31, 4 and 1 is 5, 6, 7, so that's the 7. 3 and 2 is 5, 6, 7, 8, 9. That's the 97 people that were in the sample space. And that's how we can use a Venn diagram to solve a problem. And suppose I could be asked then, what's the probability of finding a student? I can be asked, what's the probability of a student taking maths but not chemistry? Well, I can look at my diagram. Remember, let's go back. A naught intersection B, A intersection B naught is this region here. So M intersection C naught is going to be this region here. So the probability of a student that takes maths but doesn't take chemistry is going to be 34 out of 97. Okay, time for you to have a go, so pause the video now and see if you can solve this problem. 2/3 of pupils in a class have a mobile phone, half have an MP3 player, quarter have neither. What proportion have both? Okay, hopefully you've had a go at that. Let's pull up the solution and maybe I'll talk you through it. I know that 2/3 have a mobile phone, which I've denoted P. Half have an MP3 player, which I've denoted M. So if I add, and I also know that 1/4 have neither. So if I add all the proportions I have, 2/3 plus a half plus a quarter, that gives me 8/12 plus 6/12 plus 3/12. That means I get 17 out of 12. That means that 5 out of 12 were counted twice. So that's how I know that the intersection is 5 out of 12. And then working backwards, I know that 8 out of 12 had a phone. If there's 5 out of 12 here, that means there's 3 out of 12 left. Similarly, if I know that 6 out of 12 have a mobile phone, 6 out of 12, and I know that 5/12 are already in this section here, this region, that means 1/12 must be left. And that's the diagram completed. And once you complete the diagram, the questions are relatively easy to answer. Okay, let's have a look at a more complicated example now. So suppose I'm given these probabilities here, and I'm asked to work out, I'm asked to fill in the Venn diagram. So let's go through it piece by piece. I know that probability of A, the total probability of this region is 0.6. Probability of B, which is this region here, the total probability is 0.5, and so on and so forth. A intersection B is 0.3, so that would be this section here. This total section is going to be 0.3. I'm also told that A intersection C is 0.1, so this section here, this region here, where A and C intersect is 0.1. A intersection B intersection C is 0.1. So where all the three circles overlap, where they intersect, which is this region, is 0.1. And finally, I'm told that not A and not B and not C, or A complement intersection B complement intersection C complement, is 0.1. In other words, the piece outside the Venn diagram is 0.1. Right, so now I can start to fill in my information. So I know that this is the outside of the Venn diagrams of the circles or regions. Okay. I'm also told that where the three circles overlap, i.e. this part, A intersection B intersection C, is 0.1, so I can fill that in. That's 0.1. Now, how can I use what I have so far to try and help me solve the problem? So let's keep working backwards. Well, I'm told that A intersection C, which is this region here, is 0.1. Well, if I know that this part is 0.1, that means that what's left, let's put that back in, 0.1. So that's what the bit that's left must be 0, because the total probability for A intersection C is 0.1, and that still holds true. And A intersection B intersection C is 0.1, so that still holds true. So we're good with these three so far. Right, what about this? A intersection B is 0.3. So this region here, where A and B intersect, is 0.3. If this part is 0.1, that means this bit must be 0.2. What else can I work out now? Can I work anything about C? Not quite yet. And B, also not quite yet. What about here? I'm told that the probability of A is 0.6. Well, that means the total probability for this region must be 0.6. So 0.2 and 0.1 is 0.3. That means that this region must be 0.3. So the total probability of A is now 0.6 if I add them all together. How about B now? I'm told that the total probability is equal to 0.5. But I've got two missing regions. I'm also told about C that the total probability is 0.3, but I also have two missing regions. So what I like to do in this scenario now is put a little label in each area. So I'm going to call this A, little a, this region little b, and this region little c. Now, remember, the total probability of the whole sample space must equal 1. So if that's 0.3, that's 0.2, 0.1, and 0.1, adding these all together, we get 0.5, 0.6, 0.7. That means these last three bits must be 0.3. So A plus B plus C must equal 0.3. Okay, let's do that again. Because all the blue adds up to 0.7, and all that's left are these three bits. That means A plus B plus C must equal 0.3. Okay, now I'm told the total probability of C is 0.3. Well, I have some of it already, but I don't know what A and B equal. So if I know that's 1 or 0.1, that means A plus B, what's left, A plus B must be equal to 0.2, because the total probability of this region C is 3. That's 0.1, that means these two must be 0.2. Now I can start to solve my problem. I know A plus B equals 0.2. And if we look at our first equation here, well, if this bit here is 0.2, that means C must equal 0.1. So let's fill that into our diagram now. That's 0.1. Now can I finish off B? I sure can. 0.1, 0.2, 0.1 gives me 0.4 altogether. The total probability is 0.5, so B must be 0.1 also. And now that I know what B is, looking at this equation, A plus B equals 0.2, I now know that B is 0.1, so A must also be 0.1. And that's my Venn diagram completed. Okay, time for you to have a go now. Pause the video and see if you can complete the Venn diagram. This one is slightly trickier, but the same principles apply. Okay, hopefully you've had a go at that. Here is the solution. I'll briefly run through it. I started by filling in, I know that not A and not B and not C is 0.1, so this part out here is 0.1. I'm also told that B intersection C is 0, so where B and C intersect must have a total probability of 0. That means both regions are 0. I'm told that A intersection B is 0.2. Well, if that's 0, that must be 0.2. I'm told that B is 0.5. Well, if that's 0.2, that must be 0.3 because the total probability is 0.5. And then what I did was I labeled the other bits A, B, and C. So I counted up what I had. 0.2, 0.3, and 0.1 gives me 0.6. That means A, B, and C have 0.4 to fill out. Right, there's 0.4 left because the total probability of the sample space is 0.4. So A plus B plus C is 0.4. A plus B must be 0.3. That means that C equals 0.1. Now that I know C, I can work out B and A as given. Okay, that's it for this video. You should now be able to have a go at exercises 5A, 5B, 5C. Do bear in mind that in these exercises they put the same problems, but they word the problems. So they'll start talking about maths has a probability of whatever, chemistry has a probability of whatever, and physics has a probability of whatever. And you tackle the problems in the exact same way that you tackled this example here. So they're done in the same way. Just formulate the problem and see if you can complete those exercises. That's all for now. Hopefully you enjoyed the video. I hope you found it useful. I'll be back again with a new video soon. Thanks for listening, and I'll talk to you again sometime.